Hi, folks. Pepe Le Pew here, and this is statistics lesson is on extrapolating and lurking variables and whatever else we have coming up. But let's take care of this board problem right here. So let x represent a random variable whose distribution is normal. Okay, normal is important. Okay, so you got a bell-shaped curve with a mean of 100, standard deviation of 10. So which of the following is equivalent to the probability that x is greater than 115? All right, let's just draw the standard normal curve right there, okay? Mean is 100 right there. Okay, so 115 is over here, and greater than means shaded to the right. So that would be this picture right there. There's the probability of it being greater than 115. All right, so if you think of this, you guys, whatever happens on the right happens on the left, because this normal is important, you guys, means it's symmetrical right here. So if this is 15 to the right, if I go 15 to the left and shade the left-hand side, that would be my picture over there. Okay, so there would be 15 to the left over there, and that equals the probability that x is less than 85. Can you see this red area is equal to that blue area right there? So it looks like choice C right there. Dun, dun, dun. All right, so let's go ahead. Extrapolating lurking variables and using averaging data. All right, so correlation and regression only describe a linear relationship. Correlation measures the direction and strength of a linear relationship between two variables. All right, correlation and least square regression lines are not resistant to outliers. Outliers will change it quite a bit. So regression lines describe how a response variable y changes as an explanatory variable x changes. Let's see, it's hard to see that right there. There we go. All right, so always plot your data and to see if you have any influential observations or any incorrectly entered data. So you always do that, and if you take the AP test, they won't give you like 20 or 25 points to enter. It'll be like, 8, maybe 10, most 10 points to enter. So you can check your data really quickly to make sure there isn't anything, that you bubbled in something incorrectly. Okay, so always plot your data. All right, to give yourself a bird's eye view of what's going on right there. Make sure you entered it all correctly. Then extrapolating occurs when you use your least square regression line that your calculator calculated for you for predicting a response variable, a y variable. That would be far outside your x variable, so past it. So many times these aren't accurate. So for example, you guys, say you wanted to do a least square regression line on a child's growth. And you plot some how much they grew between the ages of 3 and 8 years old, and you make a least square regression line of the the 3-year-old, the 4-year-old, the 5-year-old, and so on all the way up to the 8-year-old. You make this least square regression line, and you get your y equals mx plus b line on that. And then you use that to predict the height of a 25-year-old, and you get an 8-foot tall person. Well, why would that be? Well, it's because you grow really fast between 3 and 8, and you slow down when you get to be, I don't know, about 20 something, you guys. So you stop growing basically by the time you're 25, except if you're growing outwards like sometimes us older folks do. Okay, lurking variables falsely suggest a strong relationship between x and y, or they can hide other lurking variables in your relationships. So for example, in my class, I gave a handout on airline companies, and on airline companies I showed them statistics where one company was on time more than the other company for the whole record on that. And then when you broke down between the cities, say company A was better overall than company B on flights being delayed or being on time. And then when you broke it down in between each city, you found out that actually company B was better than company A in every city that they flew from. It's just that company A flew from a sunny airport where they hardly had very many delays, and company B didn't fly so much from the sunny airport. They flew more from a rainy, foggy airport, so they had more delays. But company A, who flew out of the foggy airport, didn't fly too many flights out of that. So when you looked at the overall statistics, it was deceiving right there. All right, so discrimination in medical treatment. So I want you to read and discuss with your groups the example of 410 is found on pages 226 and 27, and here it is right here. Studies show that men who complain of chest pains are more likely to get detailed tests and aggressive treatments such as bypass surgery than are women with similar complaints. So is this association between gender treatment due to discrimination? So if you go, you find out that there's a lurking variable in there, and the lurking variable is that men and women develop heart problems at different ages. Women, on the average, are between 10 and 15 years older than men. So aggressive treatments are more risky for older patients, so doctors tend to hesitate to advise them because they're older. Doctors don't like to work on older people as much because their great work doesn't last as long. Okay, so the lurking variable is the patient's age and condition. So it may explain the relationship between gender and the doctor's decisions. So as the author of one study, the issue said, when men and women are otherwise the same and the only difference is gender, you find treatments that are, end up being very similar. All right, so this one took me a couple of times to read it and reread it to understand, and so I underlined the important part. So measuring inadequate housing. So read and discuss with your groups example 411 on pages 227. So a study of housing conditions in the city of Hull, England, measured a large number of variables for each of the wards in the city. Two of the variables were a measure X of overcrowding and a measure Y of lack of indoor toilets. What the hard part was, as Y increased, then the lack of indoor toilets became a bigger problem. So there was less toilets basically for the amount of people. Okay, so because X and Y are both measuring inadequate housing, we expected a high correlation, but they only got a correlation of 0.08. And so what happens is, on this lurking variable is this. Investigation found that some poor wards had a lot of public housing, and so these wards had a high value of X but a low value of Y, because remember, the lower the value of Y means you have more indoor toilets, and so public housing always included indoor toilets. So the higher the public housing was, the more toilets they had. And then they had other poor wards that lacked public housing, and these wards had a high value of both X and Y. So within the wards of each type, there's a strong positive association between X and Y. And analyzing all wards together ignored the lurking variable, the amount of public housing, and hid the nature of the relationship between X and Y. All right, so then they did a graph on this right here. So this figure shows a simplified form of how to the form by lurking variables can make correlations and regressions misleading. The groups appear as clusters of points in the scatter plot. There's a strong relationship between X and Y within each cluster. So in fact, you get R to be 0.85, and here R was 0.91. I think this one's the 91 here, and this one's the 85. Okay, and then however, because of the similar values of X corresponds to quite different values of Y in the two clusters alone, it's a different value for predicting. So the correlation for all the points together was much smaller. So this figure, the variables in the scatter plots have a small correlation, even though there is a strong correlation within each cluster right there. All right, that one's a little bit harder to see. All right, so you're going to just look for some lurking variables, and if you're in my statistics class, that would be your wonderful homework assignment. Take care.